Math 2312, section 1.2, domain and range, graphing piecewise functions. In the previous video, I introduced the concept of a piecewise function. What I neglected to mention is that I call them Frankenstein functions. We take a little bit of this function, we take a little bit of that function, we sew them together. How do we know which one to use? That depends on the input and the conditions imposed on each part of the function. And by the way, a piecewise function can have more than two pieces. I've seen piecewise functions with 6 and 7 pieces. They're a little annoying, but whatever. But how do you graph these things? Well, I'm going to work on the presumption that you can graph a regular function. For example, f of x equals x minus 3, either by connecting dots, by generating connecting dots, or by recognizing things like this is in slope-intercept form, and I can take advantage of that, or by recognizing that this is a parabola. But how do you graph a piecewise function? In general, there's two ways to graph a piecewise function. Graph each piece separately and then just put them on one graph, or graph each function in its totality separately and then erase the part that you don't need. I'm going to choose the second option, where we think about each of these functions' graphs in their entirety, but then we only keep the parts based on the conditions imposed on them. For example, f of x equals x minus 3. You could graph that either by using a table of values, or, as we'll review later, you can take advantage of the fact that it's in slope-intercept form, meaning that its y-intercept is at -3, so that would be down here. Its slope is 1, so it would be a perfect diagonal line. Not drawn too perfectly there. So this blue one is y equals x minus 3. And the other one, which I'll draw in red, is also a line. It's in slope-intercept form, so I can sketch it by saying the y-intercept is 0 and the slope is -2. So run 1, rise -2, and it would look something like this. Now, if you're not up to speed on slope-intercept form, that's okay, because you can generate both of these graphs just by making tables of values. But we don't keep both lines in their entirety, because first off, together they would not be a function, it would fail the vertical line test. But secondly, these functions are only defined on certain domains for certain x values. For example, the function x minus 3 is only used when x is greater than or equal to 2. That means that you take the blue line, and forgive me, I didn't label the red line, y equals -2x plus 1. But the blue line, y equals x minus 3, is only valid when x is greater than or equal to 2. That means you have to find out where this starts. This graph starts at x equals 2. If we put 2 into here, 2 minus 3 is -1. So 2 -1 would be right here. And we only want the part of that graph where x is greater than or equal to 2. In other words, numbers to the right of 2, which means we would erase this part of the blue graph. For the red graph, we only want it for x is less than 2. So we're going to stop it at 2, but I want to know exactly where it stops. I know 2 doesn't belong to the domain for the bottom part of the graph. In other words, I know when x equals 2, I don't put it here because it says x is less than 2. But I need to know where this graph stops. So I am going to put 2 in there, but make sure to represent on the graph that it's not really part of the graph. If I were to take this boundary point of 2 and evaluate it here, I'd get -2 times 2 is -4, -4 plus 1 is -3. That means that the red line stops at the point 2, -3. But that's not actually part of the red graph, because I don't actually get to put 2 in here when x equals 2. So I need to remove this point, and to remove it, I just replace it with an empty circle. It was important to put 2 into the bottom function, even though the bottom function's domain doesn't include 2, because we needed to find the boundary point for the left half of the graph. And this would be a graph of this piecewise function. When x is less than 2, it's this graph, not including its boundary point. And when x is greater than or equal to 2, it's this graph, including its boundary point. Let's do the same thing over here. For g of x equals x squared, I think most of you guys know that that's a parabola, so we're not going to do much hooting and hollering there. There it is. But let's go ahead and just keep the part that we need. This parabola is only valid when x is greater than 0. Now, I know it doesn't say greater than or equal to 0, but to find the boundary point where this graph begins, I need to put in 0 just for a moment. When I put in 0, I get out 0. Of course, that's the origin. However, it's not part of the parabola because this doesn't allow x to equal 0. And because this domain part of the function is only for x greater than 0, we want the right half of the parabola and not the left half. For the other part of the function, that's for when x is less than 0. Again, you can graph this line by either making a table of values or taking advantage of other information like slope-intercept form. Slope-intercept form here, the y-intercept would be 2. And the slope would be 2, so if we went backwards, one rise and one run, it would look like this. So the line would look like that. But this graph is only for x less than 0. Just like before, I'm going to go ahead and put in 0 for x, even though it's excluded from the domain, because I need to figure out where this function ends. In other words, where's its boundary point, if you will. The boundary of this inequality is at 0. If I put in 0, I get 2 times 0 plus 2, which is 2. So this graph ends on the y-axis, but doesn't include that point on the y-axis. Notice we needed an empty circle at the end of the red graph and at the beginning of the blue graph because neither of these functions allowed x to be 0. But again, we needed to evaluate them at 0 to see where the graphs ended and began, even though the end and beginning of the graphs weren't actually part of the graph. So it's not really that tricky to grasp the concept of graphing a piecewise function. You basically graph them all and just keep the portions that you need according to the conditions imposed on the x for each part of the piecewise function.